Good morning. Take my mask off so you can hear me better. I'm Dr. Bill Stewart, and we're going to be doing some physics and physical science today, working on motion and focusing on a very important set of equations called the kinematic equations of motion. So if you take physics or physical science, you'll want to understand how things move from one place to another, and you'll want to be able to predict like how long it'll take to go a certain distance, or what might be your final speed if you accelerate for a certain amount of time, or you brake your car. Say you were in a highway patrol position and you were investigating an accident, and you could look at skid marks, and from the length of those skid marks you could infer how fast the vehicle was going before the driver slammed on his or her brakes. So those are the kinds of problems that we do in the kinematic world. Later on we'll get into the field of dynamics, and that's where we bring in Newton's laws of acceleration, mass, and force. But right now we're going to be looking at the general motion of objects in the real world. So we're first going to define a few terms, not many. Then we're going through the derivation of the equations of motion, and then we're going to solve two problems that use the equations of motion to predict things that we might have an interest about. Okay? So let's first start with our variables. When we talk about motion, there are basically four variables that we need to address. The first is displacement, which is symbolized by the variable x, and we'll write that down, displacement. Now, you might think, well, why don't you just use the word distance? The reason is that three of these quantities that we're going to define for motion are vector quantities, and a vector is a quantity that has both magnitude, how far you have gone, but also direction, like going from Zanesville to Columbus. Going on Interstate 70 means you're pointing west. Now, in many problems of using the kinematic equations, you really don't have to worry too much about the vector, the directional characteristic of a vector, but we're going to define it as a vector and use it as we go forward. Okay, so x will be the displacement, or how far something has gone, realizing that there's a direction involved to that. Then we will have v, which is velocity, and that velocity is going to be the speed in which you are moving, again focused with a particular direction. Okay, so speed that you read on your speedometer tells you how fast you're going, doesn't necessarily tell you in what direction unless you also have a compass on your instrument panel. Okay, but velocity will be how fast we are changing where we are. Okay, so if we start from one spot and go to another spot, the time that it takes to get there will indicate how fast we are going. If we can go a certain distance very quickly, then we're going at a higher velocity. If we're going more slowly, we will be at a lower velocity. Okay? Now, in a lot of motions, we also have a change in velocity, and that is called acceleration. We use that A for that symbol. Okay? And that just indicates how fast you're changing your velocity. If you're not changing your velocity, then there's no acceleration. You're going at a constant speed or constant velocity. If you are in a hot racing car, say at a drag race, and when you release the energy of the engine, you will find yourself pushed back in your seat with a tremendous force, which is nothing more than you want to stay still, but the car is moving, so on your back in the seat, you're going to feel a great push against you in having you go with the car. And that would be a very high acceleration, okay? And finally, we are going to put time into our analysis, okay? So we have displacement, how far we're going and in what direction. We have velocity, how fast we're going and in what direction. We have acceleration, how fast are we changing our velocity or our acceleration. And we have time that sort of keeps track of everything and relates all of these together. So those are our four variables. Now we're going to develop our kinematic equations. Now the first thing we're going to do is define acceleration in terms of these other variables. So we're going to say A is equal to, well, if you have two velocities, and we'll call that V1 your final velocity minus V0 your initial velocity. The subscripts just allow us to keep track of two different velocities because they're changing. And if we divide that by t, t being the duration of the motion, okay, starting from 0t to some t 3, 4, 5 seconds hence, then we have this first equation which we can then convert using a little algebra. We can multiply both sides by t and then rearrange our variables, and this becomes v1, our final velocity, is going to be equal to v0, our initial velocity, plus a times t. A times t. So let's see how we might use this. If we know what our initial velocity is, and if we know what our acceleration is, and we know how long we're going to be doing that acceleration, meaning changing the velocity, then that'll tell us how fast we're going at the end of that acceleration phase of our motion. So that is our first equation of motion. Okay, now the second thing we'll do is we'll look at how do we find the average velocity. So V average, well, the way you get an average is take the endpoints, add them together, and divide it by 2. So we will take V1, our final velocity, we'll add that to V0, our initial velocity, and we'll just divide that by 2 to find the average, okay? Now, from this expression, we can also say that the distance we travel is going to be equal to our average velocity times our time, okay? So we know our average velocity is 3 meters per second. We go for 5 seconds, 3 meters per second times 5 seconds, 15 would be our answer for that in terms of how many meters we actually travel, okay? So this implies that x equals v average times t, which I can then plug in this for average, and I'll have x equal to parentheses v1 plus v0 over 2 times t. Okay? So this was our first kinematic equation. And this is our second. Now in some textbooks, you will see this as the second kinematic equation. Okay? But traditionally, we take that and convert it into our other variables so that we can find the distance, knowing our average velocity times the time in which we're traveling. Now, we have 2 additional kinematic equations, okay? And let's see how we might get that. Well, if we take this x equals v average times t, then that becomes v1 plus v0 over 2 times t. That's just this equation right there. And now what we're going to do is we're going to plug in our first equation into our second equation. So here we have a V1 equals that. We're going to plug that right in here to this V1. So let's see how we would do that. So here's V1, so let's bring that right down here. So we're going to have V0 plus AT. Okay, that's this part. Then we add the V0 from here. We divide all that by 2. We close our parenthesis, and we multiply that by T. Okay? Now, let's see how we might go about this. Let's gather the two V0s together. I'll bring that right over here. So we have V0 plus V0, so that's 2V0. We still have our plus AT, and then we'll divide that by 2 times T. Okay? So all I've done is take this and plug it into here. That gives me this. I gather the V0s together, so I have 2 of those, and I have all that multiplied by T. Now, let's go ahead and take this 2, and let's separate these two things. Okay? So this over 2, the 2's cancel, so I'll have V0, okay? And then I'll have AT, A times T, all over 2, and then I'll multiply that by T, out here. Final step, I'll bring it right up here, is V0, let me go ahead and write the X down here, that X equals V0 times T plus 1/2 A, this T times that T is T squared. Okay? So let me put a bracket around that. So what that tells us is if you want to find the displacement of an object in motion, you can find that by doing a couple multiplications and then an addition. So I'll take the initial velocity, V0 times T, that gives me a number, okay? And then I'll add to that 1/2 A times T squared, okay? A times T squared. And that will also give me a number, which will also be in the units of displacement, like meters or feet or miles. And this will allow me then to find how far we go if I know how fast I was going in the beginning, how long I traveled, and at what acceleration. So that's a very powerful formula for bringing things together and finding out how far something has traveled. Okay? So we have 1, 2, 3. We have one more kinematic equation to come up with. And what we're going to do there, and I'll do that right in this space right over here. Okay? We're going to take this original expression here, and I'm going to solve it for t. So I define acceleration is the difference in velocity divided by t. I'm just going to interplay these two, okay, algebraically. So I'm going to say, taking our first equation, I'm going to say that t is equal to v1 minus v0 divided by a. Simple algebra. So now I have that. Now I'm going to take my second equation, which was x equals v1 plus v2, all divided by 2, okay? And then I'm going to multiply that by t, which is what this is. So I'm going to multiply that times v1 minus v2, or v0, v1 minus v0. Why did I put 2 there? That's 0. Sorry about that. Okay? And then we'll divide this by a, and we'll close our parentheses. So x is equal to this times that. Now, let's focus on numerator and denominator. We're multiplying together, so we can do that. So we're going to multiply v1 plus v2 times v1, or v1 plus v0 times v1 minus v0. Now, this should bring up some memory of foiling, first, outer, inner, last, when which you've done in algebra. So I'm going to FOIL the top and this multiply the bottom. So let's see how we would do that. We take v1 times v1, that's v1 squared. Then we'll take the outer terms minus v0 times v1 plus v0 times v1. Well, a minus and a plus cancel, so the middle terms go away, and then what I have is the last, which is minus, for that minus sign, v0 squared. All divided by 2 times a. Okay? So that's what x would equal, coming down here. And finally, I can take the 2a from here by multiplying 2a here, and allowing that to cancel out, and putting 2a over here, 2a times x. And then what I'll do is bring this with the minus sign over to combine it with this, and now I'll just rearrange those so it's written in the same way. So v1 squared is going to be equal, this came over to this side, v0 squared plus 2ax. And that's our fourth kinematic equation. I'll put a all right. Now, let's look at these kinematic equations a second in terms of what variables are involved. So in this first one, we see both velocities, we see the acceleration, and we see t, but we see no x. X is not there. Okay? In this one, we have x, v1, v0, 2, and t, but what's missing? We have no a. There's no acceleration there. Okay? Down here, we have x, v0, t again, a. What's missing? Well, v1, the final velocity, is missing. The others are there. And finally, in our fourth equation, we have v1 and v0. We have a, we have x, but we don't have t. So, we really have 4 main variables, but as we develop this, v actually became 2 variables. So we have 5 variables. And what you'll notice is in each kinematic equation, you find 4 of them. So you have 4 of the variables, and you're missing 1. So from that, you can take the 3 variables you know and find the 4th. Okay? Because all 4 are in there. So in this case, I had v0, a, and t. I can find the final velocity. Here, I have v1, v0, and t. I can find the displacement. Here I have the displacement, v0, t, and a. And so from t, a, and v0, I can find x. And over here, I had v0, a, and x, that's 3, I can find the final velocity. So what that allows us to do is pick and choose which of the kinematic equations we want to use depending on what's given to us in a particular problem. And the reason I went through the derivation for you is so that you realize these are all packaged together. They all come from the same source. They all come from the same definition of variables, and they come from very simple relationships of averages and distance equals rate times time type of understanding. So those are the 4 equations. I'm going to stop for a second, clear the board, put put our kinematic equations up in the corner, and we're going to solve two interesting problems. Welcome back. We've cleared the board. I've put our kinematic equations up here to the right so we can reference them if we need to, and we will. And notice I've labeled them 1, 2, 3, 4, and the variables are there shown for our use. Okay, so the first problem we're going to solve is a simple car problem. It's going to start from a rest. It's going to accelerate for a little bit on a road, and what we're going to ask is how long does it take the vehicle under this type of acceleration and then constant velocity motion to travel 1 kilometer, 1,000 meters, okay? So we're going to make some assumptions. The car starts from rest, okay? And it's going to have an acceleration for an initial period of time. That's sort of normal. You're at a stoplight. You're not moving anywhere. All of a sudden the stoplight changes. You hit the accelerator. Off you go. And you get up to the speed, and at some point you decide I'm going fast enough, and then you finish your trip. Okay, so let's envision a finish line, 1 kilometer, 1,000 meters down there with a little tape across it, and when your car hits that tape, we're going to stop the clock, which we started when you began at the stoplight, and we're going to see how long did it take you to travel that 1 kilometer. Okay? So let's draw a little picture of that up here. So our starting point here, we'll have 1,000 meters is our trip distance. Call that displacement. And we'll say that the initial velocity was 0, so we didn't come into this track going at any speed. So we start from rest, and we want to have an acceleration, and we're going to say that we're accelerating 3 meters per second squared, okay, for 5 seconds. And that will allow us to get up to some traveling speed, some traveling velocity, and then we'll go at that until we cross the finish line, and we'll just keep track of what the clock tells us in terms of how long it took us to get there. Okay, so let's divide this up into two motions. There's an acceleration motion, and then there's a constant velocity motion. Okay, so let's do the acceleration phase. Okay, so we want to find out how long it takes us to travel this whole distance. Now we have an acceleration phase, so it'd be nice if we could find out how long we were in that phase. Well, we know that, 5 seconds, okay? And we're going to need to know how fast we were going when we came out of our acceleration phase, okay? So let's look at that for a second. If we want to know how fast we're going, we know how long we've accelerated, and we know what our acceleration rate is, we can use our first kinematic equation. So let's say that V1, the velocity at the end of our acceleration, is going to be equal to 0, which is starting from rest, okay, plus, we said we're accelerating at 3 meters per second squared, and we are doing that for how long? 5 seconds. Okay? So V1 is equal to 15 meters per second. That is the velocity we will have once we've gone through our initial acceleration. Okay? Well, how far did we go during that phase? Okay? Well, how far did we go? Well, let's see. Maybe equation 3 would help us. Now, why do we even need to know how far we are going? Because that subtracts from the total distance, so we need to know how far we went during this acceleration, so we know how much more displacement was required to finish the course. Okay? So let's see. How far did we go during this acceleration phase? Well, we have two ways of doing that. Let's use number 3. Okay, So we can say x is equal to v0t, well that's 0 because we were at rest, plus 1/2, the acceleration is 3 meters per second squared, times t squared. Well, how long were we traveling? We were going for 5 seconds, and we're going to square that. Okay? Let's see what we have here. So we have 1/2 times 3 times 25. Okay? So that would be 3 times 25 is 75 divided by 2. So that'd be 37.5 meters. That's how far we traveled during our acceleration phase. And at the end of that time, we were going at 15 meters per second. All right. So now, let's look at how much time did we spend during the constant velocity part. Okay, well, how far did we travel? Well, we started with 1,000 meters. During the acceleration, we traveled 37.5. So that's going to be 962.5 meters remaining. So if I add that to this, I will get that. Okay? Now, how long does it take us to travel this distance going at this velocity? Well, time is equal to how far we went, which is 962.5. So that's how far we went, divided by how fast we're going. And how fast we're going is 15. Okay? So I can do that little calculation. So 962.5 divided by 15 comes up to 64.17, rounded off. It's 1666 seconds. Okay? So what was our total travel time? Our total travel time would have been the 5 seconds plus this. So total travel time is going to be 64.17 plus the 5, so that's 69.17 seconds. Okay? Which would get us to the end of that particular trip. Okay? So let's review a second. We defined what we knew, what we were told. We started at rest. We have an acceleration for a certain amount of time. We decided to solve the problem in 2 pieces. One is the acceleration piece, and the other was the constant velocity piece. We had to find the velocity we were going to be traveling when we started at constant speed after our acceleration. But we also needed to know how far we were going to travel during that. So we were able to find the distance during acceleration, 37.5 meters. We subtracted that from the total course, got 962.5. Then we simply divided that distance by the velocity that we were traveling during the constant velocity phase, came up with this time, added that time to the initial time, and got our total time. Okay? So that was the car on a road, and you can make up your own problems, and you can go through accelerations and decelerations and constant speeds and all that, and you can do a host of different interesting problems that way. The second problem is going to be a falling object problem. So in New York City, what used to be the largest building back in the 30s and 40s was the Empire State Building. And it's still there. And I Googled before class here and found out how tall it was. And the height is 380 meters. Okay? So you multiply that by 3.1 and get the number of feet, so well over 1,000 feet tall. Okay, and I've been to the Empire State Building, been up the observation sort of place where you can look out through the glass. In the old days, people liked to think they could drop something off there and let it fall all the way down to the sidewalk, but as you'll see, that's not a good idea because you're basically dropping a bullet down to anything that it would hit. Okay? So we're going to ask, if we take an object, a penny, or a rock, a golf ball, whatever, and we drop it, how long will it take to hit the bottom, the pavement, and what will be its velocity when it hits? Okay? So let's do that. So let's draw a little picture right up here. So here it has a little tower on it there, and then down like that. And we said this is 380 meters. We're going to drop it, so the initial is going to be 0. Okay. We want to know two things, so question mark, time that it takes to get to the bottom, and velocity, the final velocity when it hits the pavement. Okay? So let's look at our kinematic equations and see which ones might be helpful to us. All right, so let's think about, let's find that velocity. Let's find out how fast it's going when it hits the ground. Well, this is how fast we would be going. We know it started from rest. We know the acceleration of gravity, which I'll give you in just a second. But, we don't know the time, so that doesn't work so well. Okay. Well, what else might we do? We're trying to find the final velocity. Well, maybe we could use this one. Here we have final velocity, initial velocity 0, 2ax. We know how far it's going to travel, and we know the acceleration. So the first one didn't work for us in a one-step process, but the fourth one did. Okay, so let's see what we get here. We'll say, using the fourth equation, we will say v1, final velocity squared, is going to be equal to 0, okay, plus 2. Now, the acceleration of gravity, you've probably learned in your physics or physical science course, is 9.8 meters per second, okay, and we're going to travel 380 meters, okay? So that's what our equation is going to be. We're going to take 2 times this times that, get a number. We're going to take the square root of that, and that'll tell us our velocity. So let's go ahead and do that. We'll take 2 times 9.8. That gives us 19.6. We'll multiply that by 380. That gives us 74.48. And we'll take the square root of that, and we'll get 86. So V1 is equal to 86.3 meters per second. Now, you might say, I don't have a real good feel for that. Well, one feel is, that's a football field. So think of 1 second to travel a football field. Maybe a better reference is miles per hour, okay? So what we can do is we can take this in meters per second and we can divide it by a factor to convert it to miles per hour. I happen to know that that's 0.447. If we divide that by 0.447, we're going 193 miles per hour. (193 miles per hour) Now, that's assuming that we ignore air resistance. Obviously, in these types of problems, in real life, air resists motion. Depending on its cross-sectional area, whether it's like an arrow that's pointing down or whether it's like a box that has a big sort of cushioned bottom to it, it will fall at different rates. Okay? So this would be the fastest it could go. That would be as if there's a vacuum, no air. That would be the fastest it could go. And it would be somewhat less than that, maybe 20 to 25% less, depending on what the cross-section area would be. If it were a penny and you dropped it properly and it didn't tumble, there would be very little air resistance to that. Okay? All right, so that tells us how fast it's going. How long does it take? Okay? Well, what might we do there? We know how fast it's going when it hits. We know its initial. We know its acceleration. We could solve this for time. So let's go ahead and do that. We do that right over here. Erase this. So we're going to use equation 1. We're going to solve it for t. So that's going to be v1 minus v0 divided by a is equal to t. Okay? We want the time, and in our first step we found the velocity that it's going to end up going, and so that allows us to quickly get to the time. So let's do that. So we're going to have, again in meters per second, we're going to have 86.3 minus 0 divided by the acceleration of gravity, 9.8, is equal to time. So that's not so hard. We'll take 86.3, we'll divide it by the acceleration of gravity, and we'll get about 8.8. seconds. Now, let me give you a real life example of this that I did as a parent. Our daughter, Amy, was in the ROTC, and then while she was in that program at college, she went to Fort Benning, Georgia, and went through paratrooping school. So she became an airborne soldier. As part of their training during that 3 weeks, they do jumps. They have to do 5 combat jumps out of the plane. And as parents and family, we were invited down to observe the last jump. And that last jump is where they jump out of both sides of the airplane with full combat gear, rifle, pack, all that. And they come down at about 1 per second coming out the door. So it becomes like a field full of parachutes. And part of the problem with parachuting is you got to make sure you don't get right under someone else, because you can suck their air out and the chute can collapse. So I'm sitting there and I'm thinking, how much time does a paratrooper have to figure out that we've got a problem here and to take corrective action, such as pulling your reserve chute? Okay? So I'm sitting there and I know these equations, and I also knew from their jump height, which is the same as like the blimps at sporting events, it's about 1,200 feet. Okay? So I'm sitting there going through the calculations in my head. How long does my daughter have to figure things out if something goes wrong? And it came to a little more than this, because this was about 1,200, but it was right around 8 seconds. So I started thinking 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, plop. That time goes real fast, okay? And in fact, in our last, in the last jump, there was a paratrooper who lost his air and his chute collapsed about midway down through the jump. And the training is, if that happens, you grab a hold of someone that's near you, if you can, to come down together. He tried that, that didn't work, and then he pulled his reserve chute just in time, actually. It opened and it came down safely to the ground. So that was a place where I was able to use the kinematic equations without any calculators or anything to make an estimate of what my daughter would have to do and how quickly if something went wrong. Luckily, nothing went wrong. She landed fine and got her airborne wings. So, kinematic equations, big part of physics, and have fun with the making up your own problems and solving them. We'll see you next time.